Why can radar detect airplanes hundreds of kilometers away? Why do Wi-Fi signals still reach your phone even when there is a wall between you and the router? The answer often involves a phenomenon called reflection, where electromagnetic waves bounce off surfaces and continue traveling in new directions. In the previous lesson, we learned that electromagnetic waves propagate through space, carrying energy and information. However, the real world is filled with objects such as buildings, mountains, vehicles, walls, and the Earth's surface. Electromagnetic waves rarely travel through completely empty space. When a wave encounters a boundary between two different materials, several things can happen. Part of the wave may continue into the new material, part may be absorbed, and part may return toward the original medium. This returning portion is known as a reflected wave. Understanding reflection is essential because reflected signals are present in nearly every RF system. Reflection can either help communication by creating additional signal paths or hurt performance by causing interference and distortion. Reflection occurs when an electromagnetic wave encounters a boundary and a portion of its energy is redirected back into the original medium. The amount of reflection depends on the properties of the two materials forming the boundary. If the materials have significantly different electromagnetic characteristics, a larger portion of the wave is reflected. If their properties are similar, most of the energy continues through the boundary. One important rule of reflection is that the angle of reflection equals the angle of incidence. In other words, the reflected wave leaves the surface at the same angle at which the incoming wave arrived, measured relative to the surface normal. Intuitively, reflection can be compared to throwing a ball against a wall. Instead of passing through the wall, the ball bounces back. Electromagnetic waves behave similarly when they encounter certain surfaces, although the underlying physics involves field interactions rather than mechanical collisions. Physically, consider a radar system transmitting a signal toward an aircraft. The electromagnetic wave reaches the aircraft surface, and part of the energy reflects back toward the radar antenna. By analyzing the returned signal, the radar can determine the target's location and velocity. Mathematically, reflection occurs because electromagnetic fields must satisfy boundary conditions at material interfaces. These conditions determine how much energy is reflected and how much continues into the second medium. Engineers use these principles to predict signal behavior in complex environments. Reflection is a fundamental concept in RF engineering because it affects both propagation and circuit performance. In wireless communication systems, reflected signals can create multiple propagation paths between transmitter and receiver, a phenomenon known as multipath propagation. Reflection is also critically important in transmission lines. If a load impedance does not match the characteristic impedance of the line, part of the signal reflects back toward the source. These reflections can reduce power transfer efficiency and degrade system performance. At the system level, reflection influences radar operation, satellite communications, cellular networks, Wi-Fi coverage, antenna measurements, and microwave circuit design. Engineers often spend considerable effort managing and controlling reflection effects. Reflection demonstrates that electromagnetic waves do not simply disappear when they encounter obstacles. Instead, they interact with their environment in predictable ways that can be analyzed and engineered. A common misconception is that reflection is always undesirable. In reality, many technologies rely on reflected waves. Radar systems use reflections to detect targets. Satellite systems use reflections during measurements, and wireless networks sometimes benefit from reflected signal paths when direct paths are blocked. Reflection is only one possible outcome when a wave encounters a boundary. Another important effect occurs when a wave enters a new material and changes direction. In the next lesson, we will explore refraction and discover how electromagnetic waves bend as they move between different media. In this lesson, we learned that reflection occurs when an electromagnetic wave encounters a boundary and part of its energy is redirected back into the original medium. We also saw how reflection plays a crucial role in radar systems, wireless communication, transmission lines, and RF engineering. In the next lesson, we will explore refraction and discover why electromagnetic waves bend when they pass from one material into another. If you found this useful, like the video, subscribe, and follow for the next lesson.